So what we will do is that we will quickly go into our studio and see how to find out frequent item sets and association rules, which from a small data set. We'll do that, and you can play with that library. A rules is the library that we will use. So you can play with it and see how to do the association mining in R. So let me open the R Studio first. Okay, so in the R Studio, we will use the library A rules. And what we will do is we will generate baskets. So basket 1 is equal to, so we will use the same data we have used to run our a priori algorithm, whatever we have used to calculate the frequent item sets. So we will use that. The library expects you to organize the data in a particular as transactions, so as a specific data type. So we need to convert this list, the vectors that we have initially entered, into the a specific form, which is so we can see that this is pretty much what is there in our slides, and then we can do some or can do a quick review, so you can do that. So it says there are there are four transactions of the item set length distribution. So one transaction of size 2 and four transactions of size 4. So you can see that this is summarizing. There is one transaction of size 2 and four transactions of size 4. And then it has done the one frequent items very quickly. So it sees that milk, bread, diaper, butter, coke is this is what is happening, and it is also done the length with respect to length. It has done the 5-point summary also. It has done very quickly, and so this is what it is. It found some labels. So now we will see that we want to create from this transaction some rules, and what we'll use is we will ask it to use a priori method. You can play with the parameters. I'm going to set to some parameters which work fine for me. So 60% support, then I will put the confidence at 50% confidence, and I can put min length of the rules is 2. So I can look at the rules it has generated. So it has generated 9 rules. Out of them, the 6 rules have a length of 2 and 3 rules have length of 3. And they did a 5-point summary of that. And even also for support and confidence and lift, they have done the 5-point summary. So we can inspect the rules. So the 9 rules are like bread implies diaper with a support of 60% and a confidence of 75%. We'll discuss little later what is lift. Okay, so lift is more like it will tell us whether the existence of correlation. So what happens is that if we take the confidence, we are taking P of suppose we have a X implies Y. How do we measure confidence? P of probability of X union Y divided by the probability of X. But it will all the lift will also use probability of Y. It is probability of X union Y divided by probability of X multiplied by probability of Y. So many times, if the lift is not 1, the experts say that it can't be interesting route. So whatever that be, we'll look at the lift little later. But we can see that it is giving us the routes with all the values, and I can also do something more. I can do a subsetting. I can only take the rules of a specific subset condition. So that it may be helpful in some contexts. I can also play with that, and I'll end up with or more rules if I reduce the support or confidence, or and I can also sort the rules. So this time I am listing the rules with the confidence. So so this way I will leave it to you people to play with this library and do the association rule mining. With there are many data sets which you can, if you wish, you can create your own simple data set. Uh, but then there are many other data sets. So for example, we have not used the data set in a textbook. Textbook does it with one data set to do. So you can carry out the association rule mining on, using the R story. Okay. So now let's start some of the. We will look at. We will analyze and see how good has been our experience with the a priori algorithm, and what can be a problem there, and is there a way we can get a better representation of the rules, and which is given that we deal with very large. So we will see whether there are more smarter ways of representing item sets on rules. So some of the challenges that we have seen, why the complexity is a problem is, it depends on the minimum support threshold. If we increase the minimum support threshold, naturally the number of frequent item sets will reduce. So if we choose a low value, then there will be more frequent item sets and more number of candidates and greater length for frequent item sets. And if the item set length increases, we need more iterations. Suppose we want to find out using a priori algorithm item sets of size six item sets which are frequent. So we need to scan the database at least 6 times. So that is required, because each time the frequent item size increases, that is the way a priori works. It works one step at a time. So if somehow there is a database which requires, which possibly has some frequent item sets of size 35, so you need to scan the database 35 times. If it's a large database, scan can be very costly. Scanning, because the database stays in the secondary memory, which is like a disk, and reading from the disk, it's going to take significant time. So if you want to do association analysis with a large frequent item set, you may have to wait for hours or days to get the result, because it's going to become very slow. But you will play in RStudio with only small data sets, so you may not experience, but then you need to understand that when you want to do real world problems. So some of the considerations are like this. So how do you choose the minimum support threshold? Then the dimensionality of the data set. So if we have more number of items, we need more space in the memory to store the support count. If the Because the memory is main memory is the place from which the computer does most of the processing. So if suppose you ended up with a database which is very big, and then we have many items, so it cannot store in the memory, so it will start writing into the disk, and it is going to become very slow. See, the point is that you may want to try out many options before you choose one. As you can see, we could play with some options and get different results. So if we wanted to change the lift so that we'll have a separate set of rules, subset of rules. But if we want to play with all those kind of things with a large databases, then you may end up with hours. So if each run takes 10 hours, I'm sure you will not be comfortable playing with many options, because that will take 1 month for you to complete this task. So for that reason, we need to be worried about the dimensionality, as that will increase the computation and the IO costs. Then size of the database, we need to scan the database once for each iteration in the a priori. So once so that means for each pass we need to scan, so that will increase and then the database size is large. If the number of transactions is large, so scan time will be large. So average transaction width. So the transaction width can increase, and that means the traversal through the hash tree, you have to travel through the more nodes, and if that tree depth itself may increase because there are more items. And so the point is that once the length of the frequent item set increases, and the transaction width will increase, and traversals through the hash tree will increase, so all of them will contribute to inefficiency or higher time complexity. So it requires more time to do the task, so which we do not want to, because if we can quickly do the iterations and get the results, it will be good. So one of the possible things that we can think of is, suppose we have a database which has got 100 items, okay, and so what that means is that if there are 100 items, so we know that how many candidates will be there all through, or essentially how many sub patterns will be there. So it will be 100 C1 plus that will come to approximately 10 to the power of 30 sub patterns, which is not a very comfortable state for even supercomputer. So if you give so much data to process, so that will also say that require days, not minutes or hours, for completing the task. So we can think of some way in which we will not have to deal with so many candidates. So one of the technique tricks that is done is to closed frequent patterns and maximal frequent patterns. So now let's look at the definitions for what is a closed frequent pattern and what is a maximal frequent pattern. A item set is considered closed if the item set is X, which consists of some items. In this case, let's say A5, A7, A23, A34, and A95. So suppose this is the item set. So it is considered frequent if there is no superset such that which contains proper superset, which is Y, which contains completely X and has the same support as X. So that is to say, we do not want to take interest in milk, let's say milk, comma, bread has a support of is equal to K, or I'll say some other number which we have never used, N. N is the support count. And now, if I say that the support for milk, bread, is also N. So then what it says is that this is not so interesting because milk bread has support of N, milk bread and cheese has support of N. So then we refer to this as a closed set, closed frequent item set. This can be simple frequent item set, but we will always have more interest in closed frequent item set compared to frequent item sets. So thereby we are saying that we can get so many patterns, but we will take interest in only subset of the patterns. Then let's look at another definition, which is for the maximal frequent pattern. An item set X is considered maximal if X is frequent and there is no super pattern which is frequent. So now let us take again another example. So min support for is 3 for it to be called frequent item set. And then we can see that the support for three, okay, but support for so now we say this is a okay, so also so let's say support for milk is 3, support for milk and bread is 3, support for milk, bread, butter is 2. So that is any superset of milk and bread is not frequent. So in that case, we refer to this milk and bread as maximal pattern, maximal frequent item set. So what happens is that by using these maximal frequent item sets and closed frequent item sets, we can consider only subsets which are of interest for us for doing association tool mining. So another interesting property is that whenever we find closed patterns, closed frequent item sets, that is representing a lossless compression of frequent pattern. So that is to say, if you can list closed frequent patterns, you can also list entire set of frequent patterns. So this is, now let's look at an example to help us understand it better. Suppose there is a database with two transactions. We are taking even smaller database to solve our problem and just get better understanding quickly. So only two transactions, A1 to A100 and A1 to A50. Those are the two transactions. And now let us say minimum support is 1. So what will be the number of frequent item sets? There will be 2 to the power of 30 or 2 to the power of 1000, 100, and it's going to be many frequent item sets. But we want to find only closed frequent item sets. We will get only two closed frequent item sets. And if we want to find maximal pattern, we are finding only one, A1 to A100, because A1 to A50 has a frequent, and A1 to A100 is also frequent. Since A1 to A50 is subset of A1 to A100, so maximal pattern is only one. So the total number of patterns is 10 to the power of 30, but closed frequent item sets are only 2, and maximal frequent item sets are only 1. So now let's see a small item data set, transaction data set, 5 transactions, and 5 items are there sold by the store, and we have got 5 transactions given, like items are called A, B, C, D, E. So we start finding what are the transaction IDs in this lattice. A has 1, 2, 4, B is there in 1, 2, 3, and C is there in 1, 2, 3, 4, and so on. So now what we can do is, we can find out some of them are closed, which are maximal, and we can eliminate the rest. So now the minimum support that we are looking for is 2. Okay, so we are not interested in which has got a support of 1. So now what it means that this set is not useful. So we can see that this ACD is closed. Okay, ACD is not just closed, it is maximal. It is closed and also maximal. But the AD is okay, AC is closed, but AC has a superset ACD which is frequent. So AC is only closed but not maximal. Similarly, so we are looking at if we have to see which are closed. C is closed, D is closed, E is closed, because both the E has got so many supersets. None of them have a frequency of 3. So E is closed. Then BC is closed, which is support of 3, but nothing is below that. AC is closed, and C is closed. D is also closed, ABC is closed, and ACD is closed. So 1, 2, 3, 4, 5, 6, 7, 9 closed frequent item sets, but only 4 maximal frequent item sets. I hope the this is actually a very simple point, but it's essentially we are applying the definition on this and observing it. So if you want to look at the Venn diagram to show what are the frequent item sets, what are closed frequent item sets, what are maximal frequent item sets. So we can see that this is representing a lossless. This is a lossless representation of, but this is not. Maximal causes loss. If you have only maximal frequent item sets, you will not be able to get all the frequent item sets or even the closed frequent item sets. So it's the closed frequent item set that is giving us a significant advantage, in the sense it is giving us a lossless representation of all the frequent item sets. But the maximal can be valuable in some business contexts. Now, to look at the some of the alternatives that we have. One alternative that we can possibly consider is that instead of keeping the transactions in this transaction database with a horizontal layout, each transaction is represented in one record. So what we can do is we can convert that into a vertical layout. So for each item, we store the record IDs or transaction IDs which contain the item. And then we sort them in the sequence in the order of the number of occurrences. So A is occurring in maximum number of transactions, next is B, next is C, next is D, next is E. So if we represent this way, it is found that if this can be, this can, first thing is that it will be, we can see, for example, if we say that minimum support is 4, we can eliminate this, and we can start building the frequent item sets using the rest. So the point is that that will help us first reduce the entire database that needs to be considered. We can only consider the subset of database, and thereby we can get the efficiency. So the next we have frequent pattern trees. So this is a alternate approach to the a priori, where we are generating the candidate items and we are evaluating them for the frequent for the minimum support, and then we are proceeding further. But the frequent pattern trees, it will try to overcome that problem of a priori, where we need to do multiple scans of the database if there is a wide item set which is frequent. So what we will do is we have almost come to the end of our duration. So we will discuss this in the next class. So if there is a frequent pattern tree, we will discuss in the next class. So if there is any question with respect to this today's topic or anything else, I'll take it. So if there are no questions, then we'll stop here today, and we will start the new topic, frequent pattern trees, in the next class, that is tomorrow. So if there are no questions, then we can close the session.